some timing for the next quiz, which would be on first at 3 on Monday. So in my email, I mentioned that instead of three quizzes, we will have four quizzes so that we can take best out of best best three quizzes out of four. Okay. Because some of you were not well in any of the quiz, and some of you could not perform also perform good in those quizzes. So it's a chance for them to like score good. Okay. So I'll take an extra quiz, which would be on 10th, I guess, and that's how we'll finish this evaluation. And then there would be a major exam at the end. So what time is fine on Monday? You can suggest some timing, and then there would be no change in this timing because yeah, it's after discussing with you. So you tell me some timing on Monday. Monday 3 p.m. is fine.
Yes, sir.
Okay, so then Monday 3 p.m. would be a quiz. I'll send an email regarding that. All right, so let us start today's lecture. So in the last lecture, we had continued developing things on or concepts on eigenvalue, eigenvectors. We introduced algebraic and geometric multiplicity, and then we also saw saw a relation between algebraic and geometric multiplicity. So in the last lecture, I also gave you one exercise of an operator. For example, it was a projection operator on a finite dimension vector space, and then I asked you to find its eigenvalues, possible eigenvalues. So I'll discuss this question at the end. Hopefully you have done this. So let us start today's lecture by introducing diagonalizable operators. So if you remember at the beginning, before introducing this eigenvalue eigenvectors, our main goal was to like see whether we can, for a linear operator, can we find a basis uh, such that the matrix of T with respect to that basis is as simple as possible. And the simplest form which we one can ask for is the diagonal matrix. So the question is whether can we find a basis for a vector space such that with respect to which the matrix of the linear operator, given linear operator, is a diagonal matrix. Or in terms of matrices, we ask this question like for a given matrix A, whether we can find a matrix P such that P inverse AP is diagonal, or whether the given matrix is similar to a diagonal matrix or not. Okay, so in today's lecture we'll try to cover this topic. So let us define first what is diagonalizable operator. Okay, so let us first define. So definition of um, diagonalizable operators. So we'll parallelly develop theory for operator as well as for matrices. So let T be a linear operator. T be a linear operator on V, and we assume that V is finite dimensional. Then T is diagonalizable if there exists a basis, let's say B of V, with respect to which matrix of T is a diagonal matrix. Okay, if we can find such a basis, then we say T is diagonalizable. Similarly, we can define for matrices also. So what is diagonalizable matrices? So we write that also. Diagonalizable matrix. So suppose that we have a matrix A of size n cross n over the field F, okay, where F is either R or C. Then A is called diagonalizable if it is similar to a diagonal matrix, or if there exists an invertible matrix over the same field, matrix P of the same size and of the same field, such that P inverse AP is diagonal. Okay? That means A is similar to a diagonal matrix. Now, question is, so this is just the definition. Now the question is whether every matrix is diagonalizable, or whether every linear operator on a finite dimension vector space is diagonalizable. So what is your answer? Is every matrix is diagonalizable?
No.
No. Can you give one example? Let's say 2 by 2 example of a 2 by 2 matrix which is not diagonalizable.
0A,
Sir,
0, 0.
sir, 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 one
One
zero
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 zero zero.
Okay,
with
so
uniform
one
matrix.
zero zero zero. One of you gave this on this. One of you gave this on this example, and anybody else?
Sir, 10 0 0 1 0.
0010. Anybody else?
And one 00 0 1.
0001. Okay.
Yes, sir.
So, how many of you are agreeing that first one is not diagonalizable? Is it
Sir,
diagonalizable or not?
yes, sir, it is diagonalizable.
It's diagonalizable. Why?
Eigenvalues
So
are different.
di
There is a
Eigenvalues
two
are.
eigenvalues, and we can find
Hmm.
each vector, मतलब इनके corresponding दो वेक्टर फाइंड कर लेंगे, उसके रिस्पेक्ट में मैट्रिक्स बना लेंगे. That's why.
अरे ये सब तो हमने अभी पढ़ा ही नहीं
सर
है.
ये को डायगोनल मैट्रिक्स है तो आइडेंटिटी मैट्रिक्स से हो जाएगा फिर.
Yes. So far we know only definition. You are using some result from your previous study, but just look at the definition. So far we know only the definition. So just use that definition and answer. For example, she said that since one of the first matrix here, this matrix is a diagonal matrix. It's itself diagonal. So you just take identity as P matrix as identity, then it is similar to itself. So it is diagonalizable by definition. Similarly, for the third matrix, how about the second matrix here? Is it diagonalizable? Is it diagonalizable?
Sir,
So the first example will not work. Third example will not work. How about the second one?
It
So
is
this
not diagonal.
example, it is not diagonalizable, but why? Just you have to use the whatever knowledge we have so far from the previous lecture or from today's lecture so far. No
सर
result, nothing.
डायगोनलाइजेबल है.
Diagonalizable hai. And one of you
सर
said,
एक
some of you said that it is not. So you are contradicting each other. So you want to convince each other. So he is true.
मैट्रिक्स 0 1 1 0 ले लेंगे तो हो जाएगा.
You are saying you take some matrix, let's say 0. P matrix is 0,
0 1 1 0.
0, 1, 1, 0. Then can you can you see whether P inverse AP is diagonal or not?
सर 1 मिनट.
Yeah, just check. It won't. I mean, it won't satisfy this. So basically, this matrix is not diagonalizable. Why this is not diagonalizable? Because
Sir,
suppose that
it's
it is diagonalizable. Yeah. Yes.
sir, it's eigenvalue not as are zeros, so it is not diagonalizable.
No, zero जरूरी नहीं है zero वाली. So zero matrix itself is diagonalizable. So if you just consider this zero matrix, by definition it is a zero, it's a diagonal matrix. So it is diagonalizable. So zero eigenvalue होने से just you cannot say singular matrices can also be diagonalizable. As in the first example, in this matrix is diagonalizable and it is singular. It has zero eigenvalue. That argument won't work. Anything else?
सर अगर
Yeah.
डिफरेंट इगन वैल्यूज हो तो भी डायगोनलाइजेबल होगा.
सिर्फ तो ही डायगोनलाइजेबल होगी, ये तो पता नहीं, ये तो हमने अभी तक पढ़ा भी नहीं है. So you're using some result which we have not learned here so far. We don't know that yet. We'll see क्या होगा.
सर आइगन वैल्यूज
Yeah.
फील्ड को बिलोंग करनी चाहिए.
So assume that it is over C.
यस सर.
Then so this matrix is over C. Let's say all these entries belong to C.
हेलो सर.
This yes.
सर ज्योमेट्रिक मल्टीप्लिसिटी कम हो गई अलजेब्रिक मल्टीप्लिसिटी से, इसलिए डायगोनलाइजेबल नहीं होगा.
पर ये रिजल्ट तो हमने अभी तक देखा ही नहीं. So we haven't seen any result yet so far. You have to give your argument using this knowledge which we have discussed in the whatever things we have discussed so far in the lectures.
So
So you are using some result which we don't know yet. Yeah.
सर इन
so
जनरल
suppose
इनवर्टेबल मैट्रिक्स देते हैं ए एक पी और पी को फिर पी और गिवन मैट्रिक्स और पी इनवर्स से मल्टीप्लाई करवाते हैं तो कोई एबीसीडी की कोई वैल्यू नहीं मिलती.
नहीं
Equal-
मिलती. So वो बोलना थोड़ा सा टफ होगा. तो वो तो ठीक है, तुम बोल रहे हो कि ऐसा नहीं होगा क्योंकि if because I said that it is not diagnosable, so you cannot find such a p. You are just using the negation of the matrix, but that argument is not like it's a vague argument that it is not. So you have to give you have to give a proof. Like take a so you say if you want to use this argument, then you say okay, take a matrix P, any invertible matrix P, then P inverse AP cannot be diagonal. You have to prove that then if you want to say this. But if you want to use by contradiction, that is possible. For example, let me do this. Suppose that this matrix is diagonalizable. Let us call this matrix A. Okay. Suppose that this matrix is diagonalizable. If this matrix is diagonalizable, then there exists by definition there exists a P invertible such that P inverse AP is diagonal. Right? This D would be diagonal. But we know that similar matrices have the same eigenvalue. This from the lectures. Similar matrices have the same eigenvalues. So eigenvalues of A are there are two eigenvalues, both are 0. So if this matrix is similar to a diagonal matrix, then the possible diagonal matrix would be this one, because it should have two zeros, two eigenvalues, both are 0, right? But then if this A matrix is similar to a 0 matrix, then A has to be 0, because then you write this as PDP inverse. D is 0, so it should be 0. When you multiply D, which is a 0 matrix, to any matrix, it is 0. So it gives A is 0, but you know that A is not 0 if A is not equal to 0. So it cannot be diagonal. That way you can answer. So here you have an example of a 2 by 2 matrix. You can generate other examples also using the same idea. So this matrix is not diagonalizable. So we have one example. In fact, you can also see this example. Let's say this one, 0, 1,
सर
-1,
मिटाइए
0.
मत.
Sorry,
सर उसे इरेज मत कीजिए।
किसको? वो आर्गुमेंट जो मैंने दिया उसको,
यस
वो तो
सर।
रिकॉर्ड anyway it is recording, and that is the argument that you can also explore. It's just a simple one line argument. Now look at this matrix. If I look at this matrix over R, so suppose that this is the matrix over R. Now this is the matrix which we obtain by, let's say it's a sort of rotation kind of thing, rotation matrix, right? So if you look at this matrix, and this matrix doesn't have any eigenvalue. Now using that also you can you can use similar idea to say that this matrix is not diagonalizable, because we know that this matrix doesn't have any eigenvalue. I mean real eigenvalue, and we are here the field is R, so it doesn't have any eigenvalue. So if this matrix is similar to a diagonal matrix, then this would be the diagonal matrix would be this one, and both the diagonal entries are real, because by definition P belongs to the same space. So P inverse P A both belong to R, and both are matrices over R. So the product would also be over R. So this is a diagonal matrix where the diagonal entries are R, belong to R. Now this implies that since similar matrices have the same eigenvalues, this matrix has two eigenvalues, but A, that means A also has two eigenvalues, or A will also have two eigenvalues, but that is not true, because we know, sorry, B, not A, B. But we know that B doesn't have any real eigenvalue, so it is not possible. So this matrix is also not possible. Anyway, but if I change the field here, if I consider, if suppose this B is over C, the entries of B belong to C, then this matrix is diagonalizable, but over R it is not. So we have seen that not every matrix is diagonalizable, and similarly you can using this you can also make construct operators, and you can say that not every operator is diagonalizable. Okay. So then the question is, okay, if not every operator is diagonalizable, then can we find some necessary and sufficient condition under which a matrix is diagonalizable or an operator is diagonalizable? So let us look at this result, and this result says that it gives us a way to check whether a given matrix is diagonalizable or not. Parallelly, we can obtain a result for operators also. So let A be a n cross n matrix over F. Then A is diagonalizable if and only if, so this is if and only if there exists a basis, of Fn consisting of eigenvectors of A. So if there exists a basis of Fn consisting of eigenvectors of A, then we can say A is diagonalizable, and the other side is true. If A is diagonalizable, we can always find such a basis consisting eigenvectors of A. The proof is very easy for this. So it's a if and only if. So proof is not that difficult. It's very straightforward. So suppose that, so it's a if and only if. So we can prove both the direction. We have to prove both the directions. So let us prove if direction first. So let us suppose A is diagonalizable. Now we have to find, using this we have to find that there exists a basis of Fn consisting of eigenvectors. Okay. So if A is diagonalizable, so since we are assuming that A is diagonalizable, what does it mean? It means that there exists a matrix P such that P inverse AP is diagonal. So let us write this matrix P column wise. So let's say these are the columns P1, P2, and so on, Pn. These are the columns of P. So this P is invertible. So this all these PIs, they are column vectors. So they belong to Fn for all I. So let P be such that P inverse AP is diagonal. Okay, because A is diagonalizable, so there exists such a matrix P. I'm writing this P column wise. So I'm denoting the first column as P1, second as P2, and so on. Such that P inverse AP is diagonal. So let's say this D matrix, the diagonal matrix looks like this: lambda 1, lambda 2, and so on up to lambda n. Okay. So these are some lambdas. So these lambdas belong to F. And they are not necessarily distinct. I'm not saying this lambda 1 to lambda n, they are distinct. Some lambda 2 might be equal to 1 lambda 1 and so on. So they are not necessarily distinct. So not, let me write this, not necessarily distinct. Okay. What I know is that P inverse AP is similar, is equal to diagonal matrix. So I'm just denoting these diagonal entries as lambda 1 to lambda n. And some of them might be repeated, but I don't care about that. So if this is the case, then what I can do, this implies that if I multiply P from left hand side, then it would be AP equal to PD, right? But then what is this? So if you look at carefully, if I multiply a matrix column wise with another matrix, for example, P, if I write like P1, P2, and so on up to Pn, this is my matrix P. So I'll write P in this way: P1, P2, and so on, Pn, and then this matrix D. D is lambda 1 and lambda n. Now, what is the left hand side here? If you look at this, the first column would be AP1. You can multiply and check that the first column of this multiplication would be AP1 when you multiply A with P1. The second column would be AP2 and so on up to APN. In the right hand side, this is a diagonal matrix. So the right hand side, the first column would be lambda 1 times P1. Second would be lambda 2 times P2 and so on. The last column would be lambda n times Pn. But then if you compare both the side, then what you get? You get that API is equal to lambda I Pi for all I. But this implies that PIs are eigenvector corresponding to eigenvalue lambda I, provided these PIs are non-zero. Can you say that these PIs are non-zero here?
Yes, sir, because it is invertible.
Yeah, P is invertible, so all these vectors are non-zero. Not only that, they are linearly independent. So this implies, so we have found n eigenvectors corresponding to n eigenvalue, and they are linearly independent. So this set S, which I denote by this, let's say P1 to Pn, collect all the columns of P. This set is linearly independent, and this also, since there are n vectors, so it forms a basis for Fn. Okay, so it's linearly independent, and hence a basis of Fn, and these vectors are actually eigenvectors. So if direction is fine, right? Now we prove the only if direction. So suppose that we have a basis consisting of eigenvectors of A. Basis of Fn consisting of eigenvectors of A. So let us suppose the basis vectors are this P1, P2. So I'm proving the only if direction. So since it has a basis, so let's say P1, P2, and Pn. P1, P2, and so on up to Pn. They form a basis. So let this be a basis consisting of eigenvectors of A. Okay, basis of Fn. So basis of Fn consisting of eigenvectors of A. And let's suppose that lambda 1, lambda 2, and so on, these are the corresponding eigenvalues. They can be repeated also. I don't know. I don't care. So let's say lambda 1 is an eigenvalue. P1 is an eigenvector corresponding to eigenvalue lambda 1. P2 is for lambda 2, and so on. Pn for lambda n. So these are the corresponding eigenvalues. Okay. Now, what we have to prove? We have to prove that A is diagonalizable. Using this, we have to prove A is diagonalizable. And how to prove A is diagonalizable? So far, we know that if we can find a matrix P which is invertible, such that P inverse AP is diagonal, then we can say that this is diagonalizable. Now, can we find using this information so far here? Can we find a invertible matrix P such that P inverse AP is diagonal? Or at least can you guess something? What P we can consider here? And then we will see whether it works or not. But at least first we need to find a matrix P which is invertible. So can you
P,
tell me?
sir, matrix
Yeah.
P distinct.
Yeah. So matrix P where the columns are P1, P2 and so on up to Pn. So we got a matrix. This matrix is clearly of size n cross n because all these columns are of size n, and this is also invertible because these columns are linearly independent. There are n columns. So, so we got a invertible matrix. Now we need to check that whether P inverse AP is diagonal or not. But that we can say by seeing AP. What is AP? So as we did here, so you just I have to repeat the same thing. So what is A and P is P1 to Pn. So when you multiply, the right hand side would be AP1 and so on up to APn. But then AP1, these are the eigenvectors we know. So it lambda 1 P1 and so on lambda n Pn. But then the right hand side we can write as P1 and so on up to Pn, and then diagonal matrix lambda 1 to lambda n. So this is actually PD. If we call this as D, then this is. But then since P is invertible, so you can say that P inverse AP, you multiply with the P inverse from left hand side, then it would be equal to D and you are done. So in order to check whether a matrix is diagonalizable or not, what you can do, you just find out the eigenvectors corresponding to distinct eigenvalues, collect their union and see if they form a they are the number of these vectors equal to the dimension of matrix or not, or the size of matrix. Then you can say, or you try to find a basis of Fn consisting eigenvectors of A. If you can do that, then you can say that the matrix is diagonalizable. Otherwise, it's not. Now, you can using this result, you can simply write as you were saying. Uh, as you were saying that some of you were saying that if the matrix has distinct eigenvalues, then so using this result one can easily derive this result as a corollary of this one. So what is this? If A is an n cross n matrix over F has n distinct eigenvalues, then A is diagonalizable. Okay, if it has n distinct eigenvalues, then A is diagonalizable. But why this is true? Why this is true?
Because we are able to find the n distinct eigenvectors corresponding to lambda is.
Not distinct, you should say n eigenvectors.
Li.
Li vector.
Vectors, because we have seen that the eigenvectors corresponding to distinct eigenvalues are linearly independent. Therefore, there would be n linearly independent eigenvectors. So they will form a basis of Fn, and therefore you can say distinct. But the converse is not true. Can you give a 2 by 2 example quickly? A 2 by 2 example where the eigenvalue, the matrix is diagonalizable, but eigenvalues are not distinct. Zero matrix, identity matrix, these are the so one of you were saying that since the eigenvalues are not distinct, it is not diagonalizable. That statement is not true, because this is only necessary, or this is only sufficient, sorry, this is only sufficient but not necessary. If it has n distinct eigenvalue, then you can say it is diagonalizable. But if it is diagonalizable, you cannot say that it should have n distinct eigenvalues. So it is only one direction. This next result, one of you were using that also, you can do using the same corollary. So if algebraic multiplicity of an eigenvalue is equal to geometric multiplicity of lambda, and this is true for all eigenvalue lambda of a matrix A, then also you can say A is diagonalizable. In fact, this result is if and only if. So you can say if this, then A is diagonalizable, or maybe you can say A is diagonalizable. Maybe I should write it as if and only if. So this is if and only if. So let A is of size n cross n over F, then A is diagonalizable if and only if and only if. So this notation means IFF means if and only if, okay? If and only if algebraic multiplicity is equal to geometric multiplicity for every eigenvalue lambda of A. If this is true, then also this. Now, can you prove this quickly using the above result? If A is diagonalizable, can you say algebraic and geometric multiplicity are equal for all the matrices, for all the eigenvalues? So you do this, okay? So we don't have much time here. So I put this as an exercise. You finish this. You complete this. Okay. Okay. So let me do one problem here. Just simple problem. Say, first you observe this. So this is an observation, but I can write this as a problem. So suppose that D is a diagonal matrix. So let D be diagonal matrix, okay, and with distinct diagonal entries, okay, all entries are distinct diagonal entries, okay, and suppose that A is another n cross n matrix F. So D diagonal matrix with all diagonal entries are distinct, and A be any n cross n matrix such that A and D commutes, okay, AD equal to DA. Then you can check that if this is the case, then A should also be a diagonal matrix. A is also diagonal. That is simple calculation. How would you prove this? So what you know, D is a diagonal matrix where all the entries are distinct. A is any n cross n matrix such that AD equal to DA. If this is the case, then A has to be diagonal. So the proof is easy. Can you give me some idea how to prove this?
Sir, A
Is any n cross n matrix such that AD, so you have to show this. So if A is a matrix such that AD equal to DA, then this implies that A is diagonal.
Sir, all entries are distinct of the diagonal matrix. तो उसके corresponding हम eigen vectors निकाल लेंगे और जो एक मैट्रिक्स कंस्ट्रक्ट कर देंगे, मतलब A को वो वाली, मतलब A जो मैट्रिक्स होगी वो आइगन वेक्टर्स की मैट्रिक्स मान लेंगे.
नो मानना नहीं है, ये है तुम्हें क्या दिया हुआ है कि एक डायगोनल मैट्रिक्स है, you also are given a matrix A such that AD equal to DA.
Yeah, sir. Clear.
This
Yeah.
AD equal to D. Now using this, you have to show that A is also diagonal. So this is not how do you do this. So what is given? You are given a diagonal matrix D. So you just write this. So assume that D is of this form lambda 1 to lambda n. These where these lambda i's are all distinct. That means lambda I is not equal to lambda j for all I not equal to j. So they are distinct. And you are given a matrix A. So let us say that A is equal to Aij. Now, if you what is and such that this A also satisfy AD equal to DA. This is given. Using this, you have to prove that A is diagonal. So you just multiply AD and DA and then compare both sides. You will see when you do this, this implies that Aij equal to 0 if I not equal to j. So that means all the off diagonal entries are 0. If you just look at this, you compare both the sides after multiplication, you get. So this is very straightforward. You don't need to construct anything. Now using this,
Sir,
why yes,
if the
yeah.
मतलब आइगन वैल्यू का जीरो नहीं होगा तो डी को अपन मतलब डी इनवर्टिबल हो जाएगा, देन आफ्टर वी कैन से कि ए डायगोनल ही होगा, क्योंकि डी इनवर्स एग्जिस्ट करेगा तो ए इक्वल्स टू ए डी ए इनवर्स, देन ए इज टू बी डायगोनल.
Why? I mean, without using this, and you are saying that eigenvalue diagonal entries should not be 0. So that assumption was also not given.
Yes sir, that's why I am wrong.
So you just look at this, and I think this should be fine. Okay. So what you are saying that D inverse AD would be A if suppose diagonal entries are all non-zero, then this is the case, and therefore A should be. But how would you conclude that this implies that A should be diagonal? That also you can conclude only after multiplying, because these two things are equivalent when D is like all diagonal entries are non-zero D. So it is the same thing. You have to multiply and then compare both the sides. Then only you will see this.
Yes sir.
Anyway, okay. So, but why I proved this? Because I wanted to use this observation, which I wrote as a problem 1. I want to use this in this form. So, if suppose we have two matrices A and B of the same size over, let's say, C, okay, and assume that B has n distinct eigenvalues. N distinct eigenvalues, and also assume, sorry, so let this B has n distinct eigenvalues and assume that AB is equal to BA. Okay, then we have to show that A is diagonalizing. It is similar to what we just did in this problem 1, but instead of saying that D is diagonal, what I'm saying that B has n distinct eigenvalues. So basically, if it has n distinct eigenvalues, that means it is diagonalizable. So B has n distinct eigenvalues and it is diagonalizable. So using this and BA equal to AB, using this you have to show that A is also diagonalizable. So how to do this? This one. So what is given? We are given that two matrices A and B, such that B has n distinct eigenvalues, or all eigenvalues are distinct, and A and B commute. If this is the case, then show that A is diagonalizable. So how to do this? So first observation is that since B has n distinct eigenvalues, so this implies
B is diagonal.
P is diagonalizable. That means there exists P um, or C such that invertible, such that P inverse AP or P inverse BP is diagonal, so let us call this D. But what would be this D? Can you tell me the diagonal entries of D? They are all distinct, right? Because eigenvalues of B are all distinct. So lambda I not equal to lambda J if I is not equal to J, right? Up to this is fine. This is just because B has n distinct eigenvalues, so B would be diagonalizable. But then we can also tell what would be the diagonal matrix. It's a diagonal matrix where the diagonal entries would be all distinct. Now, what is given next, or given is AB equal to BA. This is also given. Now, what we can do here, B matrix I can write as P D P inverse, right? So I will write it P D P inverse and then A. Okay. Then this is same as, so this implies this. This implies that I can multiply with P from left hand side. Then what it would be? P from right hand side and P inverse from left hand side. So it would be, so let me do one by one. So when I multiply P from right hand side, it would be APD equal to PD P inverse AP. So when I multiply P from right hand side. Similarly, I multiply P inverse from left hand side, then it would be P inverse AP D is equal to P, is equal to A, is equal to D P inverse AP. Now, what can you say from this? What can you say from this? So what we have a diagonal matrix here where all the diagonal entries are distinct here. And this is a matrix, let us call some matrix C. So now if you look at the previous problem, what it says that if D is a diagonal matrix where all entries are distinct, and if it commutes with A, then A has to be a diagonal matrix. Now here we have a D which is a diagonal with all distinct diagonal entries, and it also commutes with this matrix here. What does it mean? What does it imply?
Inverse
P
AP
inverse AP
diagonal.
is diagonal.
Yeah, so this implies that P inverse AP is diagonal. But what does it mean?
A
It
is
means
diagonal
A
with B.
is diagonally zero. Yeah. So it means A is diagonal. Okay. All right. So this is for matrices. We can also state a result similarly for operators. So let me write some conditions for operators also. This is a standard result which you can find in any textbook, but I will prove this so that you can at least become more familiar with the proofs. Okay. So there's the same way you can obtain a result for operators also. I will write a few equivalent conditions for operators when an operator is diagonalizable. The same way, okay, as we did for matrices. Here I'll add one or two conditions extra, but they're all equivalent. So it's
So
saying the same thing
can,
in a different way, right?
so
Yeah.
can we use here the formula AB whole inverse equals to B inverse A inverse?
Then,
Then it
but then,
then directly we can show then A is diagonalizable.
so which matrix is invertible here? P inverse AP is not invertible, na?
Why not?
P inverse, you don't know this. P is invertible, that is fine, but A is not invertible. So you don't, P is invertible, that is fine. And then you are looking at P inverse AP. Why this matrix has to be invertible if A is not invertible?
Yes, clear.
right?
Thank you.
So this matrix is not invertible. All right, so let me write this. Suppose that we have a operator T, linear operator T, our on V. V is a finite dimension vector space. So let's say assume. So let us assume that n be the dimension of V. So it's a finite dimension vector space of dimension n, and suppose that lambda 1 and so on up to lambda m. So n be the dimension, and assume that lambda 1 to lambda n, they are the, where m is less than equal to n, they are the distinct eigenvalues. Okay. So let lambda 1 to lambda m be the distinct eigenvalues. Okay. Distinct eigenvalues of T. Then the following are equivalent. So what are they? What are these conditions? First one is T is diagonalizable. Second one, there exists a basis of V consisting eigenvectors of T. This is just by definition. Third one, there exist one-dimensional subspaces W1 to Wm, or Wn, one-dimensional subspaces W1 to Wn, of V such that uh, V is the direct sum of these Wi's, and this, each of these Wi is invariant under T. But this Wi is, each Wi is invariant under T. So that means there exists one-dimensional invariant subspaces. So that the direct sum. The fourth condition is V is equal to the direct sum of eigenspaces of distinct corresponding to distinct eigenvalues. So that means E lambda 1 of T on E lambda 2 of T and so on. So there are m distinct eigenvalues. So V is the direct sum of these. This is the notation we are using. So recall that E lambda I T is what? Is the null space of T minus lambda I. So this is the eigenspace corresponding to eigenvalue lambda I. And the fifth condition is dimension of V is equal to dimension of this eigenspace corresponding to lambda 1 and so on with lambda 2 and up to lambda m. So that means sum of the dimension of the eigenspaces is equal to the dimension of V. So all these 5 conditions are equivalent. Sorry. So you can prove this. The proof is not difficult. You want me to prove this one? Or you can find it in any textbook. So if you can do it yourself, then I will skip the proof and I will move further. If you want me to prove, then I can prove it. So this is the same thing saying in a different way. You will see that it's not difficult. Okay, so we can prove. So it's not that difficult. Proof is easy. So it's these, all these conditions are equivalent. So what I will do, I will prove 1 implies 2 implies 3, 3 implies 4, 4 implies 5, 5 implies 1. This direction I will prove, and then all these conditions are equivalent. Okay. Okay, so Okay, let's do it. So let us see 1 implies 2. 1 implies 2 is straightforward, right? Because it's a definition. So if D, this is how we define na? When T is diagonalizable, an operator is diagonalizable. If you look at the definition at the beginning, T is diagonalizable if there exists a basis. Here you look at T is a linear operator, then T is diagonalizable if there exists a basis such that matrix of T with respect to that basis is diagonal, right? So uh, this is not difficult to check. You, in fact, you can, if T is a diagonalizable, then this implies that there exists a basis such that matrix of T with respect to that basis is the diagonal matrix. But you can in fact check that these vectors are in fact uh, eigenvectors. So that basis vectors are eigenvectors, and therefore that basis would be a basis consisting eigenvectors of T. So can you check this? 1 implies 2. It's very straightforward.
Yes, sir.
Yes, sir.
Okay. 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 Then let us look at 2 implies 3. Okay. 2 implies 3. What is that? So assume that there exists a basis of V consisting eigenvectors of T. Then we have to show that there exist one-dimensional subspaces W1 to Wn which are invariant under T, and V is the direct sum of these Wi's. Now, first of all, we need to find, so what is given? So let me just write what is given to us. We are given that a basis V1 to Vn. So let V1 to Vn this be a basis of V consisting eigenvectors of T. Okay. Now this is given to us. Using this, we have to form one-dimensional subspaces W1 to Wn and one-dimensional subspaces. These n-dimensional subspaces should be invariant. First, we have to construct. Then we have to see whether they are invariant under T or not. If that is also fine, then we have to check whether V is the direct sum of these W1 to Wn. But the first thing is to find these Wi's, W1 to Wn. Now, can you tell me what Wi I can consider here? I am given
Wi
V1 to
equals
Vn.
to
They are,
span of Vi.
yeah. So yes, this is the natural choice we get from what is given to us. So let us say Wj. This is the span of Vj for all j equal to 1 to n. Now this way I'll get one-dimensional subspace and one-dimensional subspaces, right? So clearly dimension of Wj is 1. And can you check whether they are invariant under T? Are they invariant under
Yes, sir.
T? These why? Why these
Because
subspaces are? Yeah,
because the T Vj equal to lambda J Vj.
yeah, yes. Because these Vj's, Wj's are span of Vj's, but Vj's are just eigenvectors. So Wj. So clearly we can say dimension of Wj is 1, and also Wj is invariant under T for all j or for each j. Okay. So you found n one-dimensional subspaces which are invariant under T. Now we just need to check whether V is the direct sum of W1 to Wn or not. Okay, this is what you need to see. But that is also true. So how to check direct sum? Let me recall. If we want to say that V is the direct sum of W1 to Wn, then what things we need to check? The first thing is that V is the linear sum of this W1 to Wn. That means V can be written as a sum of vectors from W1 to Wn. That is the first thing. And second thing is that the only way to write 0 as a linear combination of vectors from W1 to Wn is the trivial one. Can you recall this result? We have done this.
Yes, sir.
So
Yes,
we
sir.
have to we have to check these two conditions. Now why how to check the first one? So clearly W1 to Wn they are subspaces, so their sum is also a subspace, so their sum contain, so clearly we know that W1 to Wn, this sum of subspaces is again a subspace, so this is contained in V. We have to show that V is contained in W1 to Wn, right? Now how to do this? So let's say V is in V. Any element you take V. So let V in. And what does it mean? It means that can you can you use what we have and can you show that?
V can be written as a linear combination of Vi.
Yes, because they form a basis. So V can be written as a linear combination of these Vi, okay, for some alpha I in F. But then this implies that V is the sum of W1 and so on up to Wn, because alpha 1 V1 belong to W1, alpha 2 V2 belong to W2 and so on. So you can say that V belongs to this and therefore V is equal to. So you can say, let me write one more line. This implies that V belongs to W1 plus so on up to Wn, and therefore V is equal to W1 plus so on Wn. So V is the sum of W1 to Wn. Why it is a direct sum? Why it is a direct sum?
Because Vi are Li that are given to us. That is given to us.
Yes. Yes. So if you say, if you just want to use the definition, then what you have to show? You have to show that let W1 and so on up to Wn is 0, where Wi belong to capital Wi. Now, if this implies that Wi is 0, then you are done. Now, this implies that this W1 belong to V1, W1. So W1 is a span of V1. So this you can say as like alpha 1 V1, or let's say some beta 1 V1 and beta 2 V2 and sub 2 beta n Vn equal to this is equal to this, or you can say this implies this for some beta I in F. But since V1s are these V1 to Vn, they are linearly independent. This implies that beta is 0 for all I. But if beta is 0, then we can say that Wi is 0, because Wi is just beta I Vi. So this is 0. So this implies that V is the direct sum of 1 to Wi. Right? So this proves 2 implies 3. Similarly, you can do 3 implies 4. 3 implies 4. So I will leave this now. 3 implies 4 I can leave for you, so that I can at least save some time. So it's similarly you can try to prove this. If you have any difficulty, you can look at the textbook. If you are still having any doubt, you can ask me in the next class. Okay. So this 3 implies 4. 4 implies 5. This is very straightforward. 4 implies 5 is very straightforward, because this you can check the statement. 4 implies 5. So if V is the sum, V is equal to sum of these, then you can easily prove V is equal to the direct sum of these. Then clearly dimension of V is equal to dimension of. So this is because of this. Because it's a direct sum. So if you just take the union of basis of from here, then that would form a basis for V. So that means dimension of V is equal to dimension of V. So this is straightforward. And then 5 implies 1. That also you can verify. So this thing, this is an exercise for you. and this is also an exercise. So you finish this proof. Okay. The way we did this 2 implies 3, the same way you can also prove the other one. So this result gives you equivalent conditions to check whether a given operator is linearly whether a given operator is diagonalizable or not. Okay. So then the next question is, okay, we have already seen that not every matrix is diagonalizable, and similarly we have seen or similarly we can say that not every operator is diagonalizable. And what we had asked at the beginning while defining these eigenvalue eigenvectors, our aim was to say that whether we can say that every matrix is similar to a simple matrix, or whether we can find a basis of the vector space such that the matrix representation of the given operator is as simple as possible. So the most simplest thing is to look for is the diagonal matrix or a basis with respect to which the matrix is diagonal, right? But we have seen already that not every matrix is diagonalizable or not every operator is diagonalizable, right? This we have seen. So let me just write it again that recall what we saw. We saw that not every matrix or operator is diagonalizable. That we have seen, right? Because if you look at the example here, this one over R, or I gave you one more example, like you can take this one. This is over C also, you can see. So both examples you can see here. So these two matrices are not diagonalizable. Similarly, you can say for operator also. So not every operator is diagonalizable. So then the next question is, okay, if we cannot find, if a matrix is not similar to a diagonal matrix, then what is the next simple form? So what is the next simple form? If it is not
Upper
diagonalizable, then
triangle.
what we can, upper triangular or lower triangular. So we can ask for, then we can modify our question, and then we can say, okay, what can we say that a matrix is similar to an upper triangular matrix, or can we say that we can find a basis with respect to which the matrix of T is upper triangular? So this is the question which we will answer. We'll ask first and then we'll answer. So the question is, like diagonal, for diagonal matrices, we know that there are many advantages for diagonal matrix finding, like rank, eigenvalues, stress, determinant, and if even if the system is if the linear system of equation is in terms of a diagonal matrix, then solving this is also very easy. So things become easy when we have a simple matrix, and that's why we were looking for diagonal matrix. But since diagonal is not possible, then we can next ask for triangular matrix. For triangular matrix also things are not that difficult. If we have a like upper triangular matrix, let's say, then we can easily find its eigenvalues, we can find its stress, determinant, whether it is singular or non-singular. We can also easily find if the system of equation involves upper triangular matrix, then we can use back substitution to find the solution. So there are many advantages we have if we have a triangular matrix in the picture. And therefore the question is, so therefore, we want to ask this question now, that does every matrix is similar to a diagonal not diagonal, upper triangular matrix to a triangular matrix? This is the question. Triangular means upper triangular or lower triangular. We will answer for upper triangular, not a similar question. Similarly, one can answer for lower triangular also. This is the question. So does every matrix is similar to a triangular matrix? Or similar question we can ask for operators. Does there exist a basis of the vector space with respect to which the matrix of the given operator is triangular? This is the question, and the answer is, so I'll tell you the answer first, and then we'll see the details. So why this is not true? So what is your answer? You just tell me what is your answer. What is your guess for this, for a
No.
matrix? Let's say for 2 by 2. No in general.
Yes.
Yes,
Yes. Yes, sir.
Answer is yes or no?
Yes.
yes.
Answer is yes. And one of you said no. So first you tell me why it is no.
Sir, not
Give
for cross 2, for n cross n, it is no.
no for 2 cross 2 also. Then the same argument should work for 2 cross 2 also. So the in general the answer is no, because you can take the same example. No, you can take, let's say this is no. Why? Because you can take this example 0 1 minus 1 0. In general, if you look at this matrix is over R. Now, if this matrix is similar to upper triangular matrix, right? So that means there exists a matrix P. Suppose that it is similar to upper triangular matrix, then P inverse, let's say this is A. P inverse AP is upper triangular, right? This is upper triangular. But then we know that the similar matrices have the same eigenvalues. So A and this matrix, let's say U, this have they have the same eigenvalues. But this U has two eigenvalues, because diagonal entries are the eigenvalues. So that means A will also have two eigenvalues, but we know that A doesn't have any eigenvalue. So it cannot be. So in general, the answer is no. Answer is no, that not every matrix is similar to upper triangular matrix. But yes, answer is no if the underlying field is the field of real numbers. But the answer is yes if F is equal to C. So if F is equal to R, then it is not true, because we have already seen this example, one example I gave you here. But if the underlying field is the field of complex number, then you can say that every matrix is similar to a triangular matrix. We will prove this. Similar question you can answer, you can ask for operators also. Does there exist a basis for V? So let me write this question also, just for a record. So the question is, similar question for operator, does there exist a basis, or does there exist a basis of V with respect to, so V is a vector space with respect to which matrix of T, uh, sorry, matrix of T is a linear operator, is triangular. So what would be your answer here in this case?
O for
What would be the
F
answer?
equals to R, yes for F equals to C.
Yeah, no, if V is a vector space over R, so that means F is equal to R, and yes, because you can convert an example an operator using this matrix, you can answer similarly, and the answer is yes if F is over C. F is the field of complex numbers. Okay, so let us prove this one. This is very interesting because this gives us like uh, this will answer many things. We will use this result in solving other questions, because it gives us a way to do other things, to simplify many things. You will see that we will use this result in doing some other things. So this result, I will do it for um, a vector space over C, but a similar result for an inner product over C is called Schur's lemma. That is very famous result, and that is the result which is used to find eigenvalues in practice. I'll tell you that also, but let me first prove this one. So let me prove this. Let me state this result first. So what this result says? This says that if, or let's say let V be a vector space over C. Okay, this is important, and assume that it is non-zero, so n be the dimension of V, okay, which is 0, greater than 0. So the dimension of V is, so it's a non-zero vector space over C. Okay? And suppose that T is a linear operator on V. Then there exists a basis. You have to find this. I mean, we have to prove this. Then there exists a basis B of V such that matrix of T with respect to this basis is upper triangular. Now this result says that if you have a vector space over C, then every operator on this vector space can be upper triangularized. You can use similar language. That means there exists a basis of V such that matrix of T is upper triangular. Okay, let us prove this one. So what we have to do here, we have to find, so what is our target? So let me just set the things here. So what is our target here? Or what is our aim to do here? We have to do or to find a basis B. So let's say V1 to Vn because the dimension is n. So we have to find a basis B of V such that matrix of T with respect to this B is upper triangular. This is what we have to do. But if matrix of T is upper triangular, this is the same thing is equivalent to saying that matrix of T is with respect to B is upper triangular is equivalent to saying that it is equivalent to saying that where would the image of basis vector Vk would belong to? Where would the image of Vk under T belong to? What can you say about this TVK? Where would this TVK lie? See, we need that when I look at this matrix of T with respect to V, it should be upper triangular, right? Matrix of T. That means if I look at TV1, then what should be this TV1? It should be of the form alpha 1 V1 only because this is the coordinate alpha 1 or other entries are 0 here. So and so this would be alpha 1 here if I want this. Then if I look at TV2, then it can have only these two. Other entries should be 0, right? In this matrix representation. That means it can be like alpha 1 1 V1, 1 2 V1 plus alpha 1 1 V1, 1 sorry 1 2 and then 2 1 2 2 2 2 V2 and then. So these two. Similarly for TV3, only these three can be non-zero, others are 0. So what we can say from here that TVK should belong to
V1 to VK.
Linear
span of
span of
Linear span of
yes,
V1 to VK.
V1 to VK, right. So saying that matrix of T is upper triangular with respect to B is equivalent to saying that T of VK belongs to span of V1 to VK. So this is what we will prove. We will show that span of TVK, image of VK under T belongs to span of V1 to VK for each K. Take K equal to 1 to N. We will prove this by induction. So the proof is by induction on dimension of V. Okay, so this will prove by using the induction on dimension of V. Now let us set the basis for the induction. So let us suppose that the dimension of V is 1. Then is this true? The result is true. Can you find if the dimension of V is 1? Can you find a basis such that the matrix of T is upper triangular?
Yes,
Any
sir.
singleton.
Yeah, so it's a singleton, so it's a trivially true. This case is trivially. This case is trivially true. Trivially holds. So for dimension of V is equal to 1. So base case is settled now. Now assume that. So let us assume. So this is the induction hypothesis. So assume that. Let us assume that the result is true for every sorry, for every vector space whose dimension is less than dimension of V. So let us assume that for every vector space W with dimension of W is less than dimension of V, the result is true. That means, and for every uh, operator S on W, linear operator, there exists a basis B dash of W such that the matrix of S with respect to this B dash is upper triangular. So what I have written in detail is that suppose that the induction in the induction hypothesis, suppose that the result is true for every vector space whose dimension is less than dimension V. So if the result is true means what? It means that if the W is the dimension of W is less than dimension of V, and if S is any linear operator on this W, then the result is true for this means there exists a basis for W such that the matrix representation of this operator S on W is upper triangular. This is what it means, right? Now we have to use the induction step. That means we have to prove for V, which is of dimension N. Okay, so we have to prove it. We have to prove the induction step now using this induction hypothesis. So what is given? We have a vector space V over over C, and T is the linear operator. So again, let me write this. We have V vector space over C, and T is the linear operator on V. This was the case, right? T is a linear operator on V, and V is a vector space over C. So this clearly implies that. So see, we want to use the induction hypothesis, right? So induction hypothesis को use करने के लिए क्या करना पड़ेगा? We have to produce a subspace, or we have to produce a vector space whose dimension is less than dimension of V, so that we can use the induction hypothesis. But we should also produce this subspace or this vector space so that it is related to T, so that we can at least like um, we can use that and we can find a basis for this also. We can prove the induction step. Now V is a vector space over C and T is a linear operator. What can we say about the eigenvalues of this T? We can, since a vector space over C, so what we can say that this T has an eigenvalue. This is guaranteed, and that is why this result is true only for C. You remember in the proof here, in the example here I gave you, this example, this is not similar to upper triangular because this is over R, and in R there are examples where the matrix doesn't have any eigenvalue, and that is why the problem is. That is where the problem is. Now in this in the case of C, the problem that problem is no more there, because every operator or every matrix over C has an eigenvalue, and we can use that in this proof. So this implies, since V is a vector space over C and T is an operator on V, this implies T has an eigenvalue. So T has an eigenvalue. So let us call this eigenvalue, say lambda. So this lambda belongs to C. So T has an eigenvalue. Call this eigenvalue lambda. Okay, and then consider this W as range of T minus lambda I. So T is an operator, I is the identity operator. So T minus lambda I is again an operator. So let us look at this linear operator. So let us assume that W is the range space of T minus lambda I. Now Can you say that the dimension of W is less than dimension of V? Can you say this? Can you say that the dimension of W is dimension less than dimension of V?
Yes, sir.
Why?
Sir, because lambda is an eigenvalue, then null space of T minus lambda is always non-zero.
Non-zero, right? So since lambda is an eigenvalue, so let me write this. Since lambda is an eigenvalue of T, this implies T minus lambda I is not 1 1. Not 1 1. So this implies that T minus lambda I is not onto also, because they are equivalent on a finite dimension vector space. So this implies dimension of W, and W is a subspace anyway. W is a subspace of V, so dimension of W is less than dimension of. Okay. So now, if we want to use the induction hypothesis, we already have a subspace whose dimension is less than W. Now we also need to find a map which is, of course, on W, linear operator on W. So that is a linear map from W to W. If we can do that, then we're using the induction hypothesis. We can say that for that map there is a basis with respect to which the matrix is upper triangular. Okay, for that map on W, and using that basis we can construct a basis for V. That is the idea. So now next step is to construct a map or linear operator from W to W. Right. So what we can do here? Can I take the restriction of T on W? So W is a subspace of V, and T is a map. So we have V here and we have a W here, and T was given an operator. That means T is an operator from V to V. If I check whether this W is invariant under T, if W is invariant under T, then whatever image I take of W, that would go to W only. So if I check that W is invariant, so that means if T of W belongs to W, then I can take this map as restriction of T over W, right? Then I'm done. Then at least I have map. So then I can talk about this S. So now this S is actually the restriction of T. So I will get a basis for W with respect to which this S, which is a restriction of T on W, this matrix of S is, I'll get a basis for W, let's say B dash, that this is upper triangular. Then using this basis, I will find a basis for the whole space V, such that the matrix of T with respect to that basis is upper triangular, right? So what we have to do here, in order to choose T, an operator on W as a restriction of T on W, we need to ensure that W is invariant under T. Then only we can say that whatever image we take here, that goes to W only. So image of W goes to W. So T of W belongs to W only. Then we can take the restriction of T. So T is linear, so its restriction would also be linear. So this is perfectly fine once we show that W is invariant under T. All right. So let us first check that. So now we want. So next one. Now we want a map from W to W, because we want to use the induction hypothesis. So first check that if I take any vector W in W, then I can write this T of W. T of W I can write as T minus lambda times I, T minus lambda I W plus lambda I. So what I did, I have added lambda I and I have subtracted lambda, I I have added lambda w and subtracted lambda w. It's the same thing. But since w is the range of t minus lambda I, so this belongs clearly, this belongs to w because it is in the range, and w anyway belongs to w, so this also belongs to w. So what we can say from here, that t of w belongs to w, and this is for every w, every element w in w. So this implies that this t of w is a subset of w. That means w is invariant under t. W is invariant under t, and therefore we can check, we can choose. So choose as, so let S is the restriction of t on w from w to w. This is linear. So choose this map S, which is actually the restriction of t over w. Okay, or you can write this way also. Let us call this as S. Okay, so what is S? S is the restriction of t over S over w. So this is linear. This, why this is linear? Because t is linear, so its restriction would also be linear. So this is a linear. Okay. Now we have a subspace whose dimension is less than dimension of w or dimension of v, and we also have a linear operator on this w. So by induction hypothesis, there exists a basis. Let us call this basis b dash. There exists a basis b dash. Let's say w1 to wk of w, such that matrix of t restriction over w with respect to this b dash is upper triangular, right? Now we have a basis for w, and w is a subspace of v. Now what we can do, we can extend this basis to a basis of v, and then, so what I will do next, so now we have a basis for w. W is a subspace of v. So next thing is to, so our aim is to find a basis for v. So what I will do, extend b dash to a basis of v. So that means what? That means we can say that there exist vectors v1 to, let's say, vn minus k, such that this b becomes a basis. So it's a w1 to wk, and then v1 to vn minus k. These are extra vectors. This is a basis of v. Okay. Now we have a basis also of v. We have found. Now our claim is to show that matrix of t with respect to this b is upper triangular. If we show this, then we are done, right? Because this is what we are trying to do. We are trying to find a basis with respect to which the matrix of t is upper triangular. Now we already found a basis, but we don't know yet whether the matrix of t would be upper triangular or not with respect to this basis. So we have to check this. So in order to check that matrix of t with respect to this basis is upper triangular, as I mentioned earlier, I will just check that image of any vector in this basis here, image of any vector in this basis under t belongs to the span of the preceding vectors, right? So clearly you can see here t of wj, this belong to, for these wi's, because we know that these wi, they form a basis for restriction of t over w. So if I look at matrix of t with respect to this many ways, vectors, not matrix of t, but if I look at the image of t, image of w, these vectors under t, then they belong to span of w1 to wj, wj for all j equal to 1 to k. This is because of the induction hypothesis. So now we have to check that the similar thing hold for these VIs also, V1 to Vn minus k. So now check for this also. So let's say TVj. Now what I can do here, this TVj I can write as T minus lambda I Vj plus lambda Vj. So I have added in TVj, I have added lambda Vj and I have subtracted lambda Vj. Same thing. Now what is this here? This vector, this belong to W because it is the image of it is in the range of T minus lambda I, and W is the range of T minus lambda I, right? So this vector belong to W. So clearly it is in the span of W1 to Wk because this is a basis for W. And Vj, anyway Vj belongs to the span of Vj itself. So what we can say from here, that this vector Tvj, this belongs to, so this implies that Tvj belongs to span of W1 to Wk, V1 to Vj. This is true for all j equal to 1 to n minus k. But that means what? That means matrix of T is upper triangular. And we are done. Okay. So is it okay, the proof? Time is also up. So if there any doubt, you can ask in the proof. Otherwise, you can just check the proof and you can also see the recording. There is nothing special in this proof. We just use a trick that we produced a subspace whose dimension is less than dimension of V, and then we also use this given map, the restriction of a map, the given map on that subspace, and then we found a basis for the subspace and we extended that basis to the whole space, and then we check that whether with respect to this spaces the matrix is upper triangular or not, and we found that it is, and that's how we prove this. Okay. And similarly, so I proved this result for operators, but similarly you can prove this result for matrices also. So what you can say for matrices, that every square complex matrix is similar to an upper triangular matrix. So with this result I will conclude today's lecture. So this is for matrices. This is the proof can be obtained in the same way for matrices also. So every square matrix, I have proved this for operators, but similar result can be obtained for matrices also. So every square complex matrix, that means the field is the underlying field is the field of complex number. So every square complex matrix is similar to an upper triangular matrix. Okay. And you will see that this result has a lot of application. For example, you can easily prove you can use this result to prove that if you have a complex matrix of size n cross n, then the trace of a matrix is equal to the sum of the eigenvalues, and similarly determinant of a matrix is equal to the product of eigenvalues. This result you can prove easily by using this result, that every matrix is similar to an upper triangular matrix. Okay, so we can stop here. If you have anything, you can ask.
सर सर इस
Yeah.
टॉपिक पे कौन सा बुक फॉलो करनी है?
ये टॉपिक पे मैंने हॉर्न एंड जॉनसन फॉलो की थी, मैट्रिक्स एनालिसिस बाय हॉर्न एंड जॉनसन, राइट? Matrix analysis by Horn and Johnson. This book is listed in the reference book list of reference books.
ओके सर, थैंक यू सर.
Yeah. Anything else?
Hello, sir.
Yeah.
Sir, if any matrix, their eigenvalues belong to their field, then it's similar to upper triangular.
every matrix
बिकॉज सर वहाँ
if
पे
the
बिकॉज सर
eigenvalue
रियल में कर रहे थे उसकी जो आइगन वैल्यू तो निकल रही थी बट वो फील्ड में नहीं बिलोंग कर रही
हाँ
थी
हाँ राइट
तो वो
राइट राइट अगर किसी मैट्रिक्स का एक भी आइगन वैल्यू एग्जिस्ट कर रहा है फिर तुम ये रिजल्ट
sir.
ऐसा ही प्रूफ यूज कर सकते हो देन यू कैन प्रूव दैट मैट्रिक्स इज similar to upper triangular matrix.
Sir, what about Fredberg?
हाँ
Sir, what about Fredberg? उसको फॉलो कर सकते हैं?
यार ये तो मुझे पता नहीं you can do any topic so the related to answer of the question which you asked I mean before you whether every matrix is similar to upper triangular so the thing is that for complex matrices it is as we have done one can prove it but for real matrices the proof is you cannot say that every real matrix is similar to an upper triangular matrix but what you can say is that every real matrix is similar to a block upper triangular matrix where block upper triangular means either on the diagonal either we have one by one block like for a diagonal matrix here uh, not for a usual upper triangular matrix what we have this right so you can consider these diagonal entries as one by one block just one by one block right but what I'm saying that for real matrices there is a similar like analogous result it says that if the matrix is real then it is similar to a block upper triangular matrix so block upper triangular means either these blocks are of size 1 cross 1 or of size 2 cross 2 so 2 cross 2 blocks are like corresponding to the complex eigenvalues but you can prove that it is similar to a block upper triangular matrix where the blocks are either 1 by 1 or at most 2 by 2 okay so that way this proof is also there but we will not discuss this we'll focus on complex one this is just for your like information that we have a similar result for real also but it's not exactly upper triangular but it's a block upper triangular. Anything else?
Hello, sir.
Yeah.
Sir, please upload this PDF, sir, before
Yeah, I'll upload.
next lecture.
Today itself I will upload. Don't
Okay.
worry. Anything else? If
Hello,
not,
sir.
then we can stop. Yes.
सर मैंने आपको मेल किया था मुझे बात करनी
Yeah.
थी
What's your name? Abhishek.
अभिषेक मीना
Abhishek.
अभिषेक
हाँ,
मीना
Abhishek.
सर हाँ
After this class, so you stay online.
ओके
We
सर
can discuss. Okay.
ओके
So if not, then others can leave, and then we'll have a. I'll see you in the quiz. So we'll have a quiz on Monday, and then I'll see you in the next lecture on Tuesday.